Our next speaker is Nicolas, and I can see him on the screen.
Hey. Hi.
Hi, I can see your slides.
You can see my slide, you can hear me?
Yes.
Okay, perfect. So I'm going to talk about how we've worked to improve Graal reflection file generation. As you know, reflection is one of the issue on Graal, and for native image to make it completely to make it easy to use. And
sorry, Nicolas.
sorry.
Would you please introduce yourself?
Oh, sorry. Yeah, it's a very good point. I'm Nicolas, and I'm actually working on the startup called Manycore, and our product is Magicator, and we're working on Graal because we think it's a very good technology, and there is a lot of super good things to do. And this is something we've built with Marcus, who's in the audience and not talking, and we just wanted to share it with you because we felt this was interesting. So what we did is we built this tool called Magicator, and we wanted to use we basically wanted to use Graal as for native image as some kind of a platform as a service, and we tried using it, and we've run into a lot of problems. And the main one we found was really with reflection, so we decided to try to fix it. And this is kind of what we've been able to do. So we're here to kind of share what I'm here to kind of share what I've been able, what we've been able to achieve, and what are kind of our results. So the first thing we did is we used something we call slice-based analysis to kind of try to resolve reflection. And because it was actually much harder than we expected, we were able just to build a proof of concept. And that is already, as you can see online, it's already resolving instructions that GraalVM cannot. So we're able to go much further than what the dynamic agent can do, and what GraalVM can do already. And we think that's kind of one of the main problems to solve to make Graal mainstream. So we really want to. So this is a problem we're really interested in fixing. And so first, I'm going to explain what is what kind of analysis are we running. Then we're going to talk about the states of reflection in Graal. Then we'll talk about our tool and how it's working, and then sharing our results. So the first, I'll just share a couple of screenshots on what it is. It's really an online tool. You're uploading your jar, and we're giving you a configuration. And this is done without any external input. And this is a Micronaut demo app, and we're able to give you, to extract here over 148, 44 lines of the Graal config. So those are actual reflection, and we know they're actually used for Micronaut. And this is done again, it's kind of an additional compilation step. It's kind of a little bit clunky to use as it is now, but the reason is because it's just easier for us to manage. And we don't really understand we're not very good enough with Gradle to add it as a plugin for our Graal for Gradle. So the first thing it's working on is we're doing so you're familiar, I guess, with abstract interpretation. So basically, if I kind of explain it very intuitively, you execute instructions on a simplified execution model, and I kind of turn around the assumption here, and we're trying to execute a few instructions, but on the real machine. So basically, we're putting a JVM, we're picking a couple of instructions, and we're executing them, and we're trying to extract properties out of that. And interestingly enough, it's working very well for reflection analysis, and it's working also in a couple of other cases. And this is because, for what we've understood so far, is there are a lot of boilerplate code, like for instance, pushing a constant on the stack in the method that is always going to yield the same results. And there are a lot more optimizations that we can yield than what's being done out there. So, and in the case of reflection, this works very well, because reflection is really used for meta-programmation. So it's really used to kind of bind a library to an application. And it's really totally untied to the actual input of the program. So it's very different. And because of that, you can actually get really far away. And in this context, for instance, so before we get further here, one interesting idea is to kind of figure out what the status of reflection in Java, in GraalVM, especially with respect to native image. One thing I forgot to mention that's very important is in reflection is a very important problem to fix with native image because of the closed world assumption. So if you're actually missing some classes, your application will break at runtime. And the more reflection instruction you use in your program, the more that problem you're going to get. These are a couple of programs these are a couple of programs, and we just counted the number of reflection instructions in them, meaning that some will never get executed, so we don't really know, and some will get executed a couple of times. We just have no clue. But what we can see is that GraalVM, without using the agent, is able to resolve really a little bit of the instructions. And what they do by directly substitute is they're really able to reduce them to a constant. And that is clearly not enough. So it's clearly not working out of the box. If you use an external library, you want to use Graal on it, this will not work very well. You really need to make it work. That's why you have Micronaut and other frameworks that directly support Graal. But we believe there is a better way. And the first question we need to ask ourselves is, what does that mean to resolve an instruction? Especially in the context of reflection. So this is here what we really want is we want all the value of this code snippet, all the value of this variable, this class. And we need all the values, and they need to be complete, all the values and all the correct values. That's actually very complicated because you're getting, in some cases, into individual problems. So you need to kind of work a little bit around it. And right now, Graal is able to reduce a reflection instruction to constant. So in that case, this is what they directly substitute. But in the other cases, you have the tracing agent. So the tracing agent is, I'm sure you're familiar with it, but I'll just have a sentence about it. If you're going to run your app, and it's going to, each time your app is going to encounter a reflection instruction, it's just going to record it in the configuration files. The problem of it is you don't know if you have all of the values. So you just know you got some of the values, and getting all of the values is difficult, and you're never sure that you got it. So this is kind of, so this is what we need to do if you want to resolve a reflection instruction. We've tried to fix that problem in our context, which is very specific, and have a couple of additional constraints compared to what you're probably doing. And one of ours is we're using native images only for executions. So we're building native image for a specific server instance, which means that we can use a lot more optimization than if you wanted to build a jar and turn a jar into a native image and use it in a generic context. One of the obvious examples is that we can inline some of the configuration files because we already know what the values, and if they're going to change, we're going to retrigger a build. This is actually very similar to how Android is using Dalvik and ART. And this is the same idea. What they're using is, in the case of Android, they're using Dalvik, which is the format replacing the jar. They're using it to distribute the jar, to distribute their application. But to actually execute it, they're doing something called ART, which does AOT2. And they're going to compile on a specific device. So there will be an additional compilation step, and they're going to do a profile-guided optimizations. They're going to do a lot of what Graal is already doing, but tied to a device. And that idea is actually pretty powerful, and it's working. So this is kind of what we're trying to do. And because of that, we're able to extract more optimization. Another idea that sounds a little bit counterintuitive is for all what we've seen is that all reflection instructions can be fully resolved, meaning you have a reflection instruction, and in all the programs we've tested, we're always able to understand all the values it can reach without a superset or a subset. It's really the set of values. It's obviously false theoretically because you could imagine building a program where you would get the user would type something and you would try to instantiate that something into a class. So obviously you don't really know what's going to be there, but empirically this actually never happens. So we don't really know why, but it seems that people don't want to do, developers don't want to do that. We have a hypothesis as to why, but we've never found this to be false. So it's really true, and that is an optimization that allows you to go much further. So our idea is basically you don't want to have security problems. If you allow your user to type anything and execute it, this is usually security problems. And also, if you use too much reflection, then your program will be very, very hard to understand and debug. So you're also trying to limit it. So those are our hypotheses. But what we've seen so far is for normal programs, this doesn't happen, which is actually kind of, which allows you to solve that problem. And how it's working? How it's working is we're basically building a slice. So for each reflection instruction, we're going to build a backward slice. So the slice is the idea that you're going to pick a couple of instructions. Well, you'll have a seed, so you'll have an instruction, and you'll want your program to this instruction to behave exactly in the same way as if you had the whole program. So you're kind of trying to get all the exact behavior of an instruction inside a small program. I'll give you an example if it's not very clear. But the idea is a lot of them are actually easier to execute, and a lot of them are actually have no parameters, so you can just execute them as it goes. And if they do, by looking into the call graph and building recursively a backward slice, then you're actually able to work them, and they actually can be executed without an external input from the program. And once you get all of them, of course, you want to remove all the slices not linked to an entry point. And then you execute them inside the GraalVM and you get all the values you want. So I'm just going to give you two examples so it's a little bit clearer. This one is a very simple example. You have, this is one you have on our website. So you have a program that's kind of a little bit an example type of program in this that's not very useful. But this method is this code snippet is basically very self-contained, so there is no external variables, there is no parameters, so you can execute it as it is. In our case, we don't really care about what's happening after the class, this class, so we remove the last line, and we're able to gather all of the values of that class for name value, of that class variable. We just need to execute that program in the GraalVM, and we got it. Of course, real life is a little bit more complicated. So I've actually selected an example from EventBus. So EventBus is a messaging bus from it's very used. It's used a lot in Android apps. It's used also within the Java space, and it's a messaging bus to dispatch events. So, for instance, imagine that you have an app where you upload a picture and you want, like Facebook, and you want your app to update its feed. So you're going to dispatch an event to the feed and to a backup software, to a backup component and all that. That's basically very easy to use, and it's used. It's used extensively. I think they claim to have been installed in over 1 billion installed apps or something like that. So it's widely used. This is good. I just picked from GitHub. So this method is a register method. So the way it's working is you're supposed to pass yourself inside it. So for instance, you instantiate your class and you're going to register to sign up to some events. So you're going to pass yourself as a parameter. We're going to slice it, and then we're going to see how it's working. So in this case, we want to use as seed. So we want the subscribe method. This is a simplification here, but we want to use the subscribe method and we want to get all the values of it and want to have the rest of the program behaving exactly the same way. So basically, what can we remove? What kind of instructions can we remove, knowing that we want the program to behave the same way? So this is what I've put in bold. And as you can see, it's almost all of the program except an error code, which we don't care because we're okay to get a little bit of a superset of the results. So even if this wouldn't work, we would still get the values we want. So that's how we got it. And the other interesting thing is, as you can see, we have in the signature of the method, we have the subscriber method being there. So we need to extract the parameter, and we need to resolve the parameter, because otherwise we're not able to execute this program. And so what we're going to do is we're going to look inside the call graph here. So in these cases, those are my app activity 1.onResume and so on. And this, we need to slice that too, and then we'll have a working program. The idea also is EventBus is a library. Here we're basically into the application space, so we have a very concrete example, and it's going to work only in that context. So in this context, we just need to add the line, we need to rename the variable, and we're done. So if we do that and we execute this, we'll actually are going to get all the value of subscriber. This is a real example, and this works. I simplified just a couple of points. For instance, a file subscriber method uses reflection, and we will need to analyze that too, but this is actually working. And this is a program you can execute, and if you execute it, you're going to get reflection values that will be fed into that you need to build a native image. And Again, we've just built a proof of concept, so a lot of the features are still not implemented. So what we found was a good metric was to compare the tracing agent with Magicator, so our tool, and see what kind of new classes we were detecting. So first of all, they're very hard to compare because the tracing agent, you actually need to run your program. And the more you're going to run it, the more error you're going to get, the more reflection instructions you're going to trigger. Versus Magicator that you just upload your code and you got your result. So it's a little bit hard to compare. Nevertheless, so we did our best to trigger everything with the agent. And then we launched the same with Magicator. And here we got, in all cases, from all these programs, we're actually able to detect new classes that the agent is not able to detect. And this is done without input. And as a conclusion, as a conclusion, it's already working and it's already useful. So I think it's kind of a good addition to the GraalVM ecosystem because it's already generating results. It needs to be pushed further, of course. And it's and as I've mentioned in the introduction, reflection is a key problem for GraalVM to solve because if once GraalVM is able to work reliably with reflection, and then it will be easier to integrate traditional Java libraries, and then you can reuse all of the Java libraries inside Graal, and that will make it more mainstream. Also, this kind of analysis, also when you try to resolve reflection instructions, this is we can fully resolve them, which means we can basically replace them by actually their values, and we can probably also if we study that more, we think that there are these kind of semi-constant values are not very well studied, especially in compilers. So we think that there is probably more work to be done, and we can probably extract new optimizations. And also, as one of the last points is so we had to write a slicer to make that work, and this was much harder than we initially thought. And our future work, our roadmap here is we want to be able to do NPAS resolutions because right now we're not able to reach all reflection instructions. We're really stopping at the one that we can reach from an entry point. But what we've seen in most programs is that if they use reflection smartly, they're going to call reflection instructions, which will trigger another one. And that is something that the agent can capture, and we cannot yet. We just need to do several path resolution, and we'll get there. And that technique also can be, we think it can be used to fix the build time, static variables in Graal, because we can easily detect from the slice that we can build from the static variable for a variable if we can if this variable needs to be decided built at runtime or at compile time. Also, right now we're using another JVM on top of the first one to execute the slice. We have GraalVM has expressed this is definitely something we want to use. And as a last point, what we would like to go there is instead of just building the file, we'd like actually to remove the reflection instruction and replace it with its values whenever we can. So, and I'm actually done. So thank you very much. And if you have any questions, I'm happy to answer that.
Thanks, Nicolas. Are there any questions from the audience?
Thanks. I have one question. So, but do you do the slicing on the Java source code level or on bytecode, or what do you produce?
So we're actually working. We're doing it on the bytecode level because, we're doing it on the bytecode level. It's just sounded simpler and more specified.
Yes, that sounds simpler there. Yeah. And
so
then how do you?
Sorry.
Yeah. And then you generate completely new classes and run those.
Yes, basically it's exactly how we do it. The code is not very it's not very efficient, but it's exactly how we're doing it. We're basically extracting, we're running into the base system. So you have the initial code, and we're adding hours, and we're trying to find a couple of workaround to avoid losing the namespace. And yeah, we're generating new classes with new names and all that. It's actually more complicated, by the way, because it depends if you're actually going to work. Because here I kind of gave a very simple example where you put parameters. You also need to think about static variables, you think about instance variables and all that. So that kind of where it's changing. So sometimes we're going to add a method directly to the class, or some other times we're going to rebuild the class.
Okay. Any more questions? So the slicer idea is, I found it quite interesting. In general, I was wondering if there would be any benefit to using this information gathered offline with the online JIT, for example, in Hotspot. I don't know if they already do some optimizations based on the reflection.
So what I've so what I know, so in the JIT, I'm not so sure. What I've seen is there has been a lot of work to making a reflection fast on in the JIT, but there are a couple of calls that are very slow. Basically, the idea is you need to get a handle on your method. So you get the handle, and then once you have it, it's fast. Before that, it's really slow. And if you can, instead of having to grab the handle, if you can directly know it's going to, you're going to use that method or that method or that method. So basically, you replace it with a switch. The speed up is like 10 to 100 times. So so it's actually, so whether it's on Android or on the JIT in the case of the JVM, it's actually much faster to call directly. So which means that they don't do it, and you could and in the case there is another case that you didn't mention, which is the case of dynamic methods. In the case which are very similar to reflection, it's a little bit faster, but it's the same idea. It's it would go faster if you're able to get your handle directly. So if you can resolve them to, for instance, a switch with 5 different values, you have a speed up.
That's great.
And so they're not doing it. They're not doing that. Then it's actually time consuming to do it because you have to build slices, you have to execute them and so on. So there is a real impact on build time.
Okay. Thank you, Nicolas. I don't see any other questions or raised hands. So let's thank the speaker. We are coming up on a break.